Thank you everyone for coming. If you enjoyed this conference, then there will be more fun in a couple of weeks at the Congreso Nacional de la Sociedad Matemática Mexicana. Isabel and I are organizing a special session there about Theory and Harmonic Analysis, sus aplicaciones. So here you can see the speakers we have lined up. Raúl Quiroga, Isabel Hernandez, Emilio, Oswald Jardo, Gregor Weingart, Javier Sánchez, Eli, Armando Sánchez, Manuel Serrano, Carlos González, Rosendo García, Gil Salgado. Bueno, como puedes ver, a ver, ¿cuántos son asistentes a este evento? 1, 2, 3, 4, 5, 8. No, wait, so 9. There are nine of the speakers there are here as participants. So if you want to see more, it'll be at the national meetings. And I guess you can go to the webpage for the national meetings. The hours and the abstracts are already visible on the webpage. You just have to go to Congreso Nacional, and you have to click where it says ver horario, and then you have to click on the session. But so I hope that everyone who happens to be at that conference during the happens to be at the national meeting, who is interested in seeing more talks about league theory from more people from the Mexican league theory community. Hope you will have a chance to check that out. So thank you.
Thank you. It is an honor to introduce Roger Howe, who is going to give the second part of his talk on the rank of representations of classical groups. You hear all right? So last time I talked about classical groups. Okay, so there's GLN. Then there's the symplectic groups, and then there are orthogonal groups, and also there's even orthogonal groups and there's odd orthogonal groups, and there's only one odd orthogonal group, although there are two distinct quadratic forms or inner products of an odd degree, and then there are two distinct orthogonal groups of an even degree. And so something that I didn't mention, but you can do pretty much the similar thing for are the unitary groups. So I just mentioned that. So these are the examples that this theory applies to, and I'm going to focus mainly today on the symplectic group. In some ways, it's the most interesting case. Okay, so I'm going to consider representation. Sigma in SE2N. Irreducible representation of the symplectic group, and then inside the symplectic group we have this Siegel parabolic, which is a semi-direct product of GLN with the symmetric matrix group. And we want to look at sigma restricted to, well, I'll just write it as the symmetric. And then, so what we know is that the conjugation action of GLN on the symmetric matrices is the standard action. So this means that any two characters that are conjugate under GLN will occur with the same multiplicity. So in fact, you can break up the representation into a sum of these orbits, right? So we know that well, first let me indicate, so this is a sum over psi in S2 and, or Sn hat, S2 and hat of character psi occurring with some multiplicity. So this is the general decomposition of spectral decomposition for any abelian group, but because of the action of GLM, we know we can break this up into a sum over the ranks from k equals 0 up to n. So, and then there are, we said yesterday, there are two inner products in each dimension. So I will call them plus or minus. Okay. And then, and so all the characters that appear that live in a given orbit, so I'll call it O plus or minus K of psi. So O plus or minus K is an equivalence class, an isomorphism class. Of rank K. And so then if you want to know the dimension of the representation, that's just the total number of eigenvectors. So the dimension of sigma is going to be a sum from k equals 0 to n of mk plus or minus times the cardinality of this orbit O plus or minus k. Okay, and you may have wondered why yesterday I started out by counting, giving you some examples of how to count the number of points in the orbit. It's because this is what determines the contribution. So the number of points, so a given representation will either contain a full orbit or not. And so if it contains some given orbit, its dimension, it has to be at least as big as the number of points in that orbit. And so we saw that the size of the orbits increases pretty rapidly with k. This means that if you have a representation of large rank, it will have to have some pretty substantial dimension. So if you're looking for representations of small dimension, you have to look for representations of small rank. And the sizes of these orbits puts a limit on how small the representations can be. Yeah? So yeah, so we saw that in over a finite field, there are two isomorphism classes of inner products of dimension k. And so this is just some arbitrary labeling of those two inner products. Yeah. Okay, so so we want to so this is where the connection between rank and small representations arises in the fact that if you have large rank, then you're forced to have fairly large dimension. de la Peña. I reminded people that we were talking about the classical groups, and this is the list. And then I'm considering as sort of the most interesting example, the symplectic group. I want to take an irreducible representation of the symplectic group and restrict it to this abelian unipotent subgroup that's isomorphic to the symmetric matrices. And the point is that since the conjugation action of GLN creates these orbits, and the characters in a given orbit will all have to occur with the same multiplicity. And so there'll be a multiplicity associated with each orbit. So instead of having q to the n times n plus 1 over 2, you're just going to have 2n numbers, the multiplicities of those orbits. And then if you want to know the dimension, those multiplicities get multiplied by the sizes, the number of points in those orbits. And we saw yesterday that those numbers went up rapidly with k, so that a representation that has large rank that will contain characters of some large, in OK for some large k, will have to have large dimension. So this tells us that if we would like to find representations of small dimension, we should look for representations of small rank. Okay, so yesterday I went, I went through this whole lecture just to tell you what the rank of a representation was. I provided no evidence at all that this was a potentially interesting concept. Maybe all representations contain all orbits. This is although in some sense it's a significant size group, it's quite a small subgroup of the symplectic group. So maybe there aren't any small rank representations, but of course I wouldn't have been talking about it if I didn't know that there are. So how do we construct it? So let me mention in particular, let's remark that the orbits of, so O1, the size of O1 plus or minus is q to the n minus 1 over 2. So if you have any irreducible representation of the symplectic group, and it's non-trivial, then its restriction to the S2, that unipotent subgroup, will have to be non-trivial because that group generates a symplectic group as a normal. As a normal subgroup. There's no symplectic group is almost a simple group, and that you take that group and its conjugates, it generates the whole group. So you can't have a representation of the symplectic group that's trivial on the S2. So it will have to at least contain some orbit, and this is the smallest possible orbit. So this is the smallest possible dimension of a representation of the symplectic group. And actually, if you have a representation of this dimension, it will already have to be irreducible on the Siegel parabolic P, because you have this gives you this will give you a decomposition into eigenlines, one-dimensional eigenspaces, and then they all get permuted by the GLN. So a representation of this size will already be irreducible on that Siegel parabolic. So it's a very small representation. So does it exist? And the answer is yes, and this is how you construct it. So So you use the Heisenberg group. Okay, so I guess the Weyl algebra and the Heisenberg Lie algebra are very common knowledge here. The Heisenberg group is, so it's the group theoretic analog of that, and how do you construct that? So, okay, Heisenberg. So what you do is you take set let W be a symplectic vector space. Over your base field, which we are continuing to take as that. So then H of W, the Heisenberg group associated to W is just, as a set, it's the direct sum of W plus a copy of the base field, and the multiplication is, so it's, we have W and T times W prime T prime is W plus W prime. So for on the symplectic vector space, it's just addition. And we also add the T's, and then this. Then you add half of the symplectic pairing. So this guy makes it non-commutative, and you can check that the commutator. Okay, so if we call this H, so then H, and we call this H prime, then the commutator H prime, H inverse, H prime inverse, you can check is equal to 0, just W. So this group is, probably everybody knows about it already, but anyway, it's two-step nilpotent. Its center, FQ is its center, and also its commutator subgroup. And modulo FQ, of course, then it's just isomorphic to, so FQ is the center of H of W is equal to H of W commutator subgroup and H of W modulo the center is just, so it's some very mild non-abelian extension of the central extension of this abelian group. And then, so we want to look at representations of the Heisenberg group, and these are very simple to understand, and this is why also the Heisenberg Lie algebra occurs so often, I think, in representation theory. And so this originally appeared as something in part of quantum mechanics. This originally appeared actually as a theorem about the Lie algebra, but it was converted and generalized by Mackey to a theorem about groups. So I call this the Stone-Neumann math. So if you have a representation, an irreducible representation of H of W, the center is going to commute, of course, with the whole group, so it's going to have to act like scalar operator. So there will be some
So let rho be an irreducible in H of W hat. And rho restricted to the center of H of W is going to be some character pi. It's a multiple. It's going to be the dimension of rho times pi. Okay. So that's called the central character. Rho pi is the central character. And of course, I mean, this theory all works perfectly well over local fields as well, including R, which is where it originally was considered. Then any irreducible, I should say, any rho prime in H of W hat in rho with the same central character. In fact, is unitarily equivalent. So there's only one irreducible representation for each non-trivial. So we're assuming this is not equal to 1. For each non-trivial central character, there's a unique irreducible representation of the Heidelberg group. And this implies that, that the dimension of rho is equal to the size of W square root. And okay, so so this is a strong statement that and then, well, if you have a trivial central character, then the representation factors to the quotient group, which is just W, which is abelian. So those are one dimensional. So this is a description of all the non-one-dimensional representations. There's one for each character of the center, non-trivial character. Okay. I guess this is going to be and then there's lots of ways to realize this representation, and let me mention one. So what, if we break up W as a sum of two of these Lagrangian subspaces, and if you want to, you can be very concrete about this. If you write W as so if you think of W as a column vector, x1, x2, xn, y1, y2, to yn, then x can be the space where all the y's are 0, and y can be the space where all the x's are 0. And so then symplectic form is the obvious one that you write here. So then you can extend, so then x, I should say that x embeds in H of W as an abelian subgroup, as abelian subgroup. And then you can extend chi to chi twiddle. Chi twiddle of x of t is just chi of t. Okay, so you extend this character on the center to the full, so there's a character on, this is on x plus f cubed inside. So you can embed x as an abelian subgroup, and then together with the center, again, still forms an abelian subgroup. You extend the character by letting it be trivial on the x, and then, so that gives you a new character, and then rho sub chi, oh, I was going to call this, so now we'll call this rho sub chi. Since it's well defined, since it's uniquely determined by chi. And then rho sub chi can be realized as the induced representation from x plus fq to w of this chi riddle. Okay, so there are lots and lots of ways to realize this, but this is sort of a natural standard way to do it. And then the space of rho sub chi is actually isomorphic to of L2 of y. So y will form a complement to this x plus fq inside h of w, and so all of functions in this induced representation can just are determined by the restrictions to y, and you can just identify the space with L2 of y, and then y. So rho chi of y just acts. Or say rho k of y 0 of f of y prime is just going to be f of y prime minus y. So y is going to act in the usual way just by translations on L2, and rho chi of xt of f of y is going to be chi of, and I may have this may be wrong of the sign, but it's basically the inner pairing of x and y. So the point is that the group x, the group inducing group will just act by multiplication operators. We'll multiply each function at each place. So the delta functions, the functions supported at one point in y, will be the eigenfunctions for this x plus fq, and they'll all be distinct eigenfunctions. So yeah, so I'm identifying the space with L2 of y. So I've got a function on y. And then what is rho chi of y0 do to that function? It just translates it.
Right. I was just wondering if you meant to have
Oh.
prime.
Oh, here, yeah, prime here. Huh?
Well, I don't know. But where you had rho x of y prime, I thought you meant y0.
Oh, this is what I meant now. And I'll put a 1 to be consistent with both times there. Okay. So this is how it looks. You can be very explicit about it. Okay. So you have the Heisenberg group, and you have these irreducible representations of it. And then, now we observe that SP of W naturally embeds into the automorphism group of H of W. I mean, this is totally obvious, right? You just apply a symplectic transformation to the W part of, so G of W and T is just G of W. And because the group law on H is defined by the symplectic form, this is an automorphism. And so we can let the symplectic group act on the Heisenberg group, and then it's a general situation, right? If you have, if you have a group of automorphisms of a group, it also acts on the irreducible representation. It permutes them around. But since this action is trivial on the center, it will preserve the central characters, so it's going to leave each one of those roci fixed. So since SP W restricted to the center of each W is trivial, G, I'll call it G star of rho chi, is equivalent to rho chi for every G. So it looks uninteresting, but what this means is that, you move the operators. So you've got this representation of H, and you move the operators around by G, and that representation is unitarily equivalent to the original one. So you've got these two actions on the same space that are unitary equivalent. There's a unitary operator that moves one to the other. So this implies. There exists. Omega of G, and the operators I'll assume this, I'll call it the space of Y of this is the space of Y. So you can think of it as L2 of Y. So anyway, there's going to be a unitary operator such that rho of pi of W and T is equal to, G of W and T is equal to omega of G rho chi of W and T omega G inverse. In other words, in the normalizer inside the space of operators of the vector space, there's a unitary operator which accomplishes that automorphism. And since the representation is irreducible, omega of G is uniquely defined. Well, not quite. Up to the scalar multiple. Okay, so Schur's lemma says that there. So Schur's lemma says that there's always a scalar multiple ambiguity. So because of this uniqueness, we can conclude that if we have two elements of the symplectic group and we have the associated operators, that's going to accomplish the same thing as the operator given by their product. So that means that there's some scalar such that those are equal. Okay. So those scalars can be a little bit of a problem, and it means that you don't have exactly a representation of the symplectic group. You have what's called a projective representation of the symplectic group. So if you divide out by the scalar operators, then you get a homomorphism into the projective unitary group. And over a local field, this problem is, in fact, you cannot get rid of those scalars. You can get rid of them up to plus or minus 1, but you can't completely get rid of them. But it turns out in the finite field case, that you can just get rid of them. This is not a very difficult thing to show, but I won't go into the details. So there's a theorem. You can choose omega g's so that beta g prime. So this is for FQ finite. Over local fields, you can't quite do that. Okay, so that means that we get a representation of the symplectic group. That's right.
That's the central extension.
Yeah, that's the central extension.
So, well, that's a covering, and I'm guessing that since everything's discrete here, that doesn't make any sense. Is it a topological thing that's making this work out?
Well, I mean, there's a notion of covering group, in general group theory. I mean, if they're topological groups, you want to have topological considerations also. But there's a notion of central cover in group theory, and so there are examples, interesting examples of that. But I mean, just like you have, right? SL2 is a double cover of PSL2, for example. So you get a representation omega of ST of W into the space Y, which we know is isomorphic of Y. And so what is it like? Well, so it turns out, although the symplectic group is much bigger than the Heisenberg group, and it's acting irreducibly, but the symplectic group does not act irreducibly because it has a center plus or minus 1, and you can check. It's clear from the definition that the minus 1 is not going to act as a scalar operator, on the vector space. So it's going to break up into two eigenspaces. So omega, I'm going to call omega chi, as so these are eigenspaces for minus identity inside of this vector group. And you can check that, that the dimension of omega I plus or minus, well, if you set up the indices right, it's going to be q to the n minus plus or minus 1. And so with the minus 1, you have this one of these smallest possible representations, and with the plus 1, you have one dimension more. So on the Unicode on the S2N, the other one is the same rank 1 orbit plus a trivial character, and both. And also, right, I mean, this representation depends on chi, but the dependence is very weak, and it turns out it really only depends on pi up to squares, so there are two. Corresponding to the two rank 1 inner products. Okay, so we can construct, by using the Heisenberg group, we can construct representations of rank 1. And the smallest possible representation. So that's very nice, but we can go further. And so there's a general observation, which maybe I should have made before, but I'll bring it on you now. So this notion of rank, right? I mean, a basic fact of linear algebra is that if you add two matrices, the rank of the sum is at most sum of the ranks of the matrix. And so the multiplication in the group, in these Unicode groups in the dual are just correspond to matrix addition. So and so that means if you multiply two characters of this S2 group together, then the rank of their product, I mean, so the so chi s prime is just chi s plus s prime, or s prime s star, which is the same as s2. So what does this mean in terms of representation? If you take two representations of the symplectic group and you restrict them to S2n, and one of them has rank k and one of them has rank L, and if you take the tensor product of those two representations, the restriction will just be restricted to S2n. It will just contain all the products of the characters that occur in the two individual ones, which will correspond to the sums, and their representations will have rank well, those characters will have at most rank L. So here's a general observation. If sigma and sigma prime are representations of ST2N, ranks L, then sigma tensor sigma prime, okay, less than, or at most, the full representation will have rank A plus L, but it will probably not be irreducible, and the pieces will have rank less than. Okay, so that means, so we've constructed representations of rank 1. So now we can start tensoring them together and construct representations of any rank we want. Okay, so we know we can find representations. So then, so what kind of representations do you get at rank K? Okay, so to construct representations of rank K, we can take K-fold representations of a tensor. K-fold tensor of omega I. And so we can construct them, but it doesn't give us a very good handle on what they look like. So it turns out that there's a beautiful way of sort of describing what you got. If there will be characters of rank K plus L in this tensor product, yes. But the tensor product probably won't be irreducible, and some of the irreducible pieces may not have characters. May have characters strictly less. Yes. So the question is, so we can construct representations, but how can we do this in a way that we can sort of understand what's going on? And it turns out that so we can understand this process, using dual pairs inside larger support. Okay. So again, this idea is something that applies to all the classical groups, but I'll only explain it in the case of symplectic groups, so that we take our symplectic vector space again. Let's take another space. And let's let U be an inner product space. then if we take their tensor product, okay, so this is tensor product over the finite field, then W tensor U, which I'll call twiddle, as the structure. Of symplectic. Namely, so what you do is, so if you take a W tensor U and a W prime tensor U prime, and you want to look at their symplectic, you want to define a symplectic pairing, what you do is you take the symplectic pairings of the W's and you multiply that by the inner product of the U's. Okay, and this will define a symplectic form on the tensor product. And it's obvious from this formula that have embeddings SP of W goes into SP of W twiddle. So you just let W act on the first factor. We'll clearly preserve this inner product or this symplectic form, and O of U also will embed into it. So you let U act, orthogonal group act on the second factor, and it will preserve that pairing also. So you have this pair of subgroups inside the big symplectic group. And it's clear, I mean, since one is acting on one factor and the other is acting on the other factor, they commute with each other. SP W and O of U inside SP of W twiddle mutually commute. But what more is true is that in fact, if you look at SP of W inside SP double twiddle and say what is the commuton of that? What are all the elements? What is the centralizer of that? What are all the elements that commute with that? The answer is O of U, and vice versa. If you look at O of U and say what is the centralizer of that? It's the symplectic. Moreover, each group is the full centralizer. Okay. So this is a nice situation from the point of view of representation theory. So if you think about what are we doing in terms of the symplectic group, we wanted to take tensor products of these, the basic representations, which I call the oscillator representation. Most people call it the Bay representation, so I ask people to indulge me. So we take tensor products of this oscillator representation with itself, and it turns out that doing that tensor product essentially amounts to embedding SPW in a larger SPW twiddle in this fashion. So that if we look at the oscillator representation of SPW twiddle, and restricted SPW, we're looking at a k-fold tensor product of the oscillator, one copy or the other of the oscillator representation of SPW. But now we also have this subgroup of the orthogonal group inside there commuting with SP, so it can help us to decompose the representation. Okay, so that's we have the following theorem. Consider omega of S to be W critical restricted to SP of W tensor over times W. And so what I'm going to do is, anytime you have a representation of again, this is all over finite group. So anytime you have a representation of a group, you can decompose it into a sum of irreducibles. And what you can collect all the equivalent irreducibles together into one piece. It's called the isotypic component. Okay, so that's what I want to do. I want to look at the isotypic components for the orthogonal. So I'm going to have a sum over So I'm going to look at all the pieces which transform according to a given irreducible representation of the orthogonal group, and then there will be some other representation which I will call big theta of tau, where this is some representation. Since the symplectic group commutes with the orthogonal group, its action will preserve each of the isotypic components. So they will break up into the tau tensor sum representation of the symplectic group. Okay, there. Theta of tau is sum. So not necessarily irreducible. So I have that decomposition, and so the nice fact is that each one of these theta taus may not be reducible, or may not be irreducible, but theta tau contains a unique irreducible sum n of rank k. All the other sum n's have lower rank. And also, I should say also, so I'm going to give this a name. I guess I should have said before. So as a representation of the symplectic group, you can see ahead of time that it's a rank K representation, but it's also not just a rank K representation. It's rank K of the type of this orthogonal group. So there's two possible orbits of rank K that can appear in the spectrum of the S2N, and only the only rank K orbit that appears is the one corresponding to this orthogonal group, not the other orthogonal group. Okay, so we should say that this has and then let's see, a unique irreducible summand, which I'm going to call eta of tau, and then eta of tau is of type overview. Okay, so the orbit of characters of rank K that appear will all have the type, that type of overview, and none of the other type. So secondly, we get every tau, every possible tau. So the map tau goes to eta of tau is an injection of O of U back into SP of W. One thing I forgot to say, assume K less than. I mean, otherwise, it would be bigger, it wouldn't be small, right? So we get an injection of the unitary dual of the orthogonal group into the unitary dual of the symplectic group, and it's and also into the representations. So it's into the unitary dual, but it's representations of rank K and of the appropriate type. And thirdly, so there is really a close connection between tau and eta of tau, and so if you look at the multiplicity of OU in of eta of tau. So if I look at the multiplicity of the rank K characters that appear in eta of tau, that multiplicity is the dimension of tau. Okay, and unfortunately, to state the rest of the theorem, I'm going to have to paste this part of it. And then, so 4. So this means that so that the dimension. So if we look at the dimension of eta of tau, this will be at least as big as the size of that orbit, O times dimension tau. So this says just at rank K, you have this multiplicity, so it's got to have at least this big a dimension. Yeah, but that's most of it. So this is less than 1 plus epsilon of Q times rest of the representation, the smaller rank characters that appear account for a relatively small part of the representation, and the fraction is where epsilon q goes to 0 as q goes to 0. So if you think of this as depending on the size of the base field, then this factor approaches 1 as the base field that's 50. So anyway, so this piece here is almost completely fills up the representation. So that's it. So this gives a description of a very nice, orderly description of a chunk of the rank K representations of the symplectic group. And we believe that this, in fact, is all the rank K representations. We don't have a proof of that yet. It's a little bit difficult to. We have a certain amount of evidence that this should be true, but we don't have a proof. However, I should say that there's a comparable. There's a parallel theory for the other classical groups, in particular for GLN. And for GLN, the whole picture is much simpler. Okay, so the rank 1 representations that you get out of this, you get them in the same way by looking at GLN inside the symplectic group and restricting down. But the action of GLN is quite easy to understand. The oscillator representation is sort of mysterious. You can't write down all of the operators in a nice way in any given realization. But for GLN, the action is just up to a character. It's just a permutation representation on the basic vector space of GLN, F equal to Q. So it's just a permutation representation. And then the k-fold tensor product is just the action on L2 of k by n meters. And this is relatively easy to understand, and we can show for GLN that at least if the rank is sufficiently small, this accounts for all representations. So in the case of GLN, we have some result in this equation. And again, so for GLN, what happens is that you get an embedding of the rank K representation, or you get an embedding of the unitary dual of GLK times, well, there's an issue of tensoring with characters. So rank 0 representations are just characters of GLN, and then you need to tensor with characters. So you get an embedding of the unitary dual of GLN times characters of GL1 into the rank K representation. And we know that when K is small enough, that's exhaustive. I mean, for GLN? For GLN, it doesn't matter. It doesn't matter. I mean, they all give you, I mean, the one that you should choose is the one where the pieces are most equal. But if you choose any other one, if anyone says this representation is small rank, or less than the maximum possible, any other one will agree with that. There's no. So there are these representations of the small rank, and we have a very nice description of some of them, and we think that in fact is small rank. I should also mention that, yeah, so we can do the kind of harmonic analysis that I suggested at the beginning, and so elements of the symplectic group that are sort of hardest to control in terms of this, character ratio. Actually, the hardest element is just what's called a symplectic transvection. You just take one vector and shear along that vector, and it turns out that the character ratio of that guy in these representations is almost exactly, well, very close to q to the minus k over 2. So it decreases with each increase in rank, you get a decrease of q to the 1/2. We have similar results for all of So it does appear that this decomposition is definitely relevant for harmonic analysis. It's actually interesting for SL2, right? I mean, SL2 over a finite field, it's for, everybody has known the unitary dual for years, and mostly you have these principal series of dimension q plus 1, and these discrete series of dimension q minus 1. But there's these four little odd guys, of which are roughly only half the dimension. And in fact, those are the pieces of the oscillator representation for SL2. And the character ratio for all the normal representations is of the unipotent element in SL2 is 1 over 2. But for these pieces, these rank 1 pieces of the oscillator representation, the character ratio is q to the minus half. So it already for SL2, this kind of explains, it kind of adds something to the picture that why are these representations here, or what are they doing? Their harmonic analysis is pretty good. There's an oscillator representation for SL2R, and they're holomorphic representations, but they're not. One of them is not temporary.
Any other questions for the speaker? I do have a question. So for example, in this case, you are analyzing the behavior of these representations of finite groups by looking at the action of these parabolics. In the case of the symplectic case, we are looking at the single parabolic. Will it be possible to make an analysis more similar to, for example, looking at wavefront sets and Whittaker models? What I am thinking is like there is an orbit decomposition for the nilpotent orbits of these groups that's going to be periodic, right?
So let me mention that. So there will be an analog of this theorem in the local field case, and then what will happen is you'll get an injection of the admissible dual of the orthogonal group into the admissible dual of the symplectic group. And there should be a very simple relationship between the wavefront sets.
Anything else? Okay, so then let's take the speaker again.
And just an announcement for the afternoon talks. We will be, for those who weren't here for the first announcement, we will be leaving the hotel at 2:45. I will be leading everyone personally to